Okay. Jyrki is our next presenter. And his specific interest, it's not, cats or dogs or something. It's effects of nitrogen and carbon dioxide on peatlands. I mean, this is like a pickup line when in social gatherings or something, the specific interest. Do you use that?
Yes. Taking kind of emeritus elderly dogs out to the slow walk.
Okay.
That's really punchline. Okay, nice to be here. My name is Jyrki Jauhiainen, and I'm coming from Resources Institute Finland. And now we are talking about, I give you a very short overview of what kind of a methodology we used in live OrgBalt fieldwork over the past years. Let's see. Okay, you have seen this now, but I think this map here kind of shows us that we are midst of peatlands and organic soils globally, and in this region, these peatlands have formed during the past. Most of the peatlands formed during the past 10,000 years after the last glaciation period and the ice retrieval from the region. So we have a history of about 10,000 years of organic soils to form here in the Baltic Sea region, but much of the peatlands have been drained within the past 100 of years or so, or a couple of hundred of years, and formed a significant source of greenhouse gas emissions into the atmosphere. And unfortunately, it seems that globally, the drained peatlands area is still increasing. So when we wanted to learn about this soil carbon balance and greenhouse balance, the equation is very simple. Soil carbon balance is what you add, how much carbon you add into the soil, and how much carbon you lose from the soil within a certain time period. That's simple. It's quite simple where the carbon comes into the soil. It's primarily vegetation, which produces dead organic matter, litter, tree leaves, branches, grasses on the soil surface. But a lot of carbon is going below the ground surface as well. Roots are growing, roots are dying and forming as well litter. And that's something we often forget. And of course, when we go to the composting, for example, what is that? It decomposes and causes degrades and forms kind of inorganic substrates. Carbon dioxide can produce methane, nitrous oxide, and these are the greenhouse gases we find very nasty at these days. Although some of these gases are needed also to run the ecosystem. And so, actually, this is quite simple. And of course, processes are kind of controlled or steered by certain environmental conditions. So the litter characteristics, for example, how much litter is deposited, where it's deposited, what is the structure that impacts how fast this organic matter decomposes, and environmental conditions. Soil moisture, oxygen availability, which is often referred as a water level in soil, temperature, these all impact on the decomposition processes. To quantify these emissions, we have talked about the emission factor, which is a number which provides estimate of this greenhouse gas emission from defined soil area over the time in specified land use and environmental management conditions. That's quite simple. So these numbers have been discussed today. And this IPCC, Intergovernmental Panel on Climate Change, is one of the entities providing guidance and ways how to measure greenhouse gas emissions and, for example, and also soil carbon balance in organic soils in different countries. And in case people don't know what are our emissions from organic soils, there is always option 1, tier 1 emission factors available, which are compiled based on best available knowledge in a group of people and based on scientific peer-reviewed data. But this data, as was seen, the confidence limits are quite wide. So sometimes if we go out in the peatlands, drained peatlands here, it can be that the few nominators which are common to the tier 1 emission factors is okay. it's organic soil. Oh, this is a certain land use, and this is the climate area fitting to this condition. But everything else, the soil type, water conditions, vegetation characteristics. Is it a city like forest? Is it deciduous trees or conifers? What is the ground vegetation? What is the fertility of soil? It all can differ, and so we have we get a quite wide confidence limits, and that's the reason why one of the reasons why OrgBalt was created to get more accurate data for these areas. So going towards from tier 1 to tier 2 or even tier 3 emission factor levels, where we get more accurate and site type specific information from the areas. And now we finally, from my short introduction, go to the how we did it. And actually, I hope that this gives you idea. We are working in a very not stagnant root level or whatever root level. This is a outcome of the project, of this type of projects, is a hard work in the field, hard work in the laboratory, a lot of time consumed doing things. And it's quite simple things what we do, but still quite complex. So this group of people in Live OrgBalt, we plan to do harmonized data collection on different site types, and we have a lot of site types. I'm not sure if this number is correct, but let's say over 40 sites at least in the project. Different land management conditions, different setups, and that each country participating had different history of collecting data, and also the traditions were different, but we wanted to harmonize at best possible way. So we spent quite some time, like Eva said, planning the study, finding ways to make a good spatial and temporal coverage on the data collection. So we looked at literature, how much and how the data has been collected, and we wanted to find the better than average in the past. So going beyond that and improve the methodology implemented. And of course, this is a kind of pushing other upcoming or next projects doing even better, we hope. And we wanted to make as complete as possible with a reasonable resources datasets. And what these datasets are needed to create a soil carbon balance and other greenhouse gases. So about the sites and how we did on the sites. This is a brief summary of that. Here we have a green land area, that's an organic soil area in, let's say, in a forest land. We selected the most kind of a representative location there, close to the drainage ditch. And on this area, we established monitoring points. We grouped the monitoring points in a group of three locations. We can call them subplots or plots in this case. And the driving factor was, okay, from the drainage ditch, just to get kind of an understanding of how different hydrological conditions in drained soils affect on the greenhouse and soil carbon emissions. And then on each of these groups of plots, we set up quite a comprehensive monitoring setup where we looked different components. And here I want to say greenhouse gas balance in the soil is not just gases in the soil. So the gas measurements is only one part of the measurements. So we monitored greenhouse gases in different setups, collected environmental data on water tables, soil moisture, temperature, and so forth, and also mass-based data on the living parts of the system and that organic matter and matter in transitions from one phase to another. And what we did, we looked at mass-based measurements. So we have mass-based measurements and gaseous flux measurements in the study. And first we look, soil carbon balance is the soil carbon added in the soil, and the mass-based measurements here are looking the litter, which is going on into the system from above ground and below ground. And how we did it, so carbon additions from above ground litter, we spent 2 years in the monitoring sites collecting litter with the litter collectors, emptied it every time we went to the field sites, and different litter types were separated, drained, or oven drained and weighted. And vegetation community and the biomass, which was done on each side, in forest side. So making like vegetation coverage maps, different vegetation groups, looking shrubs, herbacées, vegetation, grasses, mosses, and what is the coverage percentage on the site, and they do it making biomass sampling from the areas, looking the biomass, dry biomass of ground vegetation, different groups, and then. And as I said, below ground process going on. We studied the fine root biomass from soil cores, one-time sample, looking to how much roots are in the soil, and fine root biomass production from root ingrowth socks and root net systems. So looking how fast the roots grow in certain space in the soil, in the area. And that was used for estimating the soil carbon added in the system. And then we go to the carbon loss side. We had both mass-based measurements and gaseous flux measurements over there. The liter carbon loss experiment, actually this is something what is continuing after the life of OrgBalt as well. We started a liter mass loss experiment. So we collected typical litters from the sites and made litter bags, which we put on the soil, and also the root litter below the soil surface, and follow the decomposition process of these typical litter types over the years. I think we are on year 3 on the above ground litter decomposition work, and year 2 on the below ground litter decomposition. Because a lot of this is something. From literature, you can find some values, but they are quite general. We want to verify and see how it is in the reality. Even though, so we look the existing information when we calculate the emission factors, but also want to see if this is the case so we don't agree. Okay, this is from the liter value. It's good enough, because soil carbon balance, for example, in annual basis, it's a question of a few tens of grams or few hundred grams every year. So you cannot just rely on something from the literature. It's better to have it measured on site. But it takes time and a lot of work, a lot of effort, and a lot of driving and laboratory work as well. I forgot the gaseous measurements. So we also measured gases. The teams in our project went to the field every 3 weeks, every 4 weeks throughout the year, which is quite exceptional because often these gaseous measurements are limited to the summertime growing season only. But people here went throughout the winter at best conditions. In some places you couldn't access, of course, during the winter. Some places, so then it was postponed until you could go there. We measured heterotrophic respiration from the soils from trench points, 9 points in each site. That was the goal. And then also other gases, total CO2 respiration, methane and nitrous oxide emissions in the soil from at least 5 points at each site. And the methods we used, we have Likert analyzers, EGM analyzers, and also collected gases in syringes and vials and analyzed by gas chromatography in the laboratory in some places. But that was defined by the methodology what was available at each location. Of course, this gives the soil carbon balance or greenhouse gas balance for the soil, but it would be not much worse if we wouldn't have a quite extensive environmental condition monitoring. So measuring the water, soil characteristics, and in water level is one of the drivers well known to influence greenhouse gas emissions. But we also look at the water temperature, pH, conductivity, oxygen content, and chemistry in the plots by periodic sampling. And in soil, we monitored soil temperature in different depths. And not only during the gas flux monitoring events at the field site, but we had loggers to get kind of over-year data from the site. And the soil physical and structure and chemistry was monitored by one-time sampling and the laboratory work done on the samples. So this is actually the summary. There's a lot to be done at the field work, a lot to be done over 2 years. That is considered, I think, in the IPCC says it's a 2-year monitoring is kind of a minimum. But considering the lifetime of the projects, it's a quite big part of the project already. And considering the ecosystem types, forests, one rotation of forest land, it can be 60, 70, 100 years. One project, 4 years, it's quite short. 2 years from that, it's even shorter period. So we get glimpses of the system and what's happening there, but that means that the data collection has to be started at some point, continued. The numbers we have to get, we trust, but we can always improve them in next projects and learning new things there to steer our research. So that was the last slide. Thank you very much.
Thank you, Jyrki. Oh, you had the timer here.
Yeah, yes, and
That's
I was watching that, and oh.
Yeah, that's very smart. Can you leave it for others?
No.
Okay, so a few questions through Slido. What are the key challenges in standardizing greenhouse gas measurement methodologies across different field sites, and how does your joint field methodology address these challenges?
So I think it's one thing is people or the groups start very different points. Some have no experience, some have quite a lot of experience, and more experience you have, more traditions you have also. So finding the way to combine different kind of existing methodologies and kind of experience levels is one thing, but also forests, agricultural lands, they can differ a lot, and so having kind of a comprehensive and similar enough methods implemented in different locations. So that's one challenge.
We have a few questions about potential errors in this field of science. For example, so data collection is mostly based on spot type samples, obviously.
Yes.
That may lead to uncertainty of results. So how do you comment this, and how do you avoid this affecting the results?
Okay, you have to have a reasonable, representable size plots where you measure, which reflects the vegetation type or the conditions on the site in a proper way. You have to have
is it also a number of them, or is it just the size?
Size and number, okay. And how where you put the locations, and that's in the reporting that is sometimes problem. You just get number. If you look the peer-reviewed papers, you just measured over the 5 points, but that doesn't describe how you set up the plots. And so that's one thing. Just kind of have a organized way to do things. And in this kind of project where you have tens of plots or sites included, then you have to have kind of a similar measures you can rely and not getting wild with the measurements. So.
Okay. What about integrating some remote sensing technologies?
Well, that's one thing, and here I refer to my one of the last slides, having the kind of a comprehensive environmental data collection included. And one thing is, when you set up this kind of project, you don't know beforehand what your sites are exactly like. So you have to, during the project, you measure the sites, you take the soil samples and characterize the soil quality, for example, and you learn during the project what it is there. But all that information, environmental data, temperatures, water level, especially logger-based data, and the vegetation characteristics, that's something you can combine with remote sense data, for example, and forest structure data you can use for kind of a more accurate implementation of the emission factors of certain conditions in a like a country level, for example. So you have to have kind of a measures which are linking your spot level data to wider use. So there has to be connection.
All right. Question on this. Yeah. By the way, you can put your name in it. I mean,
don't know where.
Anonymous is it's nice.
Some Andy student from somewhere.
I'm just one of the speakers today.
Okay.
Yeah. All right. So about IPCC from 2006 and 2014. So wetland supplement differs significantly for temperate climate zone. What were the main drivers for such big changes?
What to say? Thank you, Andy. Last minute. So it differs from 2006 to 2014. These emission factors. Yes. Well, of course, in 2014 we got the wetland supplement in place, and the data where what information was available, it was already organized there. So I think that could be one of the reasons. But 2006, I think it was quite early stage for forming the data collection, and so we are learning by doing. That's what I can say.
It's a long time ago anyway.
Yeah, and now we are 20 years. Yeah, and now we are 24.
Exactly.
So, and we have learned a lot since 2014.
All right. Okay. What about the vegetation above ground? Was that included in emissions balance? This is like
yes, because it's part of it's an important part of the for example, the litter production. So the ground vegetation, because it's not litter collectors. What we used, it collects the litter coming from let's say in the forest, from the trees, but the ground vegetation. The ground vegetation, the biomass there, it's formally like grasses. They are considered to decompose 1 year, so the whole biomass is lost. So that carbon is part of the annual losses already, and we get that from the biomass measures. So it's a bit small puzzle we are working on here. And that's getting the limits in the right place. We don't double count something, or we don't miss something. That's important. And I, in this limited time, I didn't have time to go to the details, but we try to measure as much as we can important things and what has meaning. So, and I hope that this data is it's kind of giving kind of a base for further studies and for more studies. And these studies are not easy to do, but demand a lot of time, and but can lead to a great achievement.
All right. Thanks so much.
Okay, thank you
for coming. Yes.
Thank you.